Hello everyone, welcome back to our tutorial 12 on simple linear regression 2. This is the last tutorial for ECON1310 Introductory Statistics for Social Sciences. So thank you so much for participating up to now. You guys have done really well, have interacted a lot, and you guys got good grades comparing to the average. So good job to everyone. Let's start with the admin part. I think I will start with the most important thing that is happening from here, which will be the LBRT3, right? It's happening during, as we're doing it, this course during summer. We will still have one revision week next week, and then finally during the exam period, we will have the LBRT3. So it will happen, let me get my favorite pen here. It will happen between the 7th of February and the 8th of February. Okay, so that means what? Let me open my little calendar. 7th and 8th, it's Tuesday until Wednesday. And for the third LBRT, you still have a second attempt, which will be open from the 9th until the 10th. So one after the other. They are the same. LBRT3 will be the same as 2 and 1, 90 minutes. And it will be from lectures 9 until 12. As well as CMLs 5 and 6. So I think that's all the information you guys need for LBRT3. If I don't see you anymore, good luck with it. It's worth 20%, so it's very important for your grade. I hope you can do both attempts to try to get the best score as possible. Next thing, just reminding you about the CMLs. The second attempt of CML 5 is still open and will be open until Friday only. So you have another 2 days to finish it. And CML 6 will be open. It will be open until Monday. It's open now and will be open until Monday. CML 6 is about linear regression. And today we're studying the last topic in linear regression. And
man.
Hey, Alex, how are you?
Hey, yeah, I'm spewing, man. I didn't realize you had a consultation at 3 to 4. I'm just checking the timetable, but it's okay. Anyway, how are you?
All good. Thank you. How are you?
Yeah, good. I also got Dominic as well sorted for this Friday to speak to him.
Amazing. No, good luck
So
with
yeah.
it. Yeah. No, fantastic. I think Peter's consultation would also be on Friday. But yeah, no, have a chat with Dominic. That's for sure.
And sorry, I didn't come. I wasn't on this Tuesday's 4 o'clock tune.
That's all good. No problem.
Sorry about that.
All good, Alex. No, thank you for coming. So coming back to CML 6, it's about linear regression, and it does replay, depending on the grade you get for it. It's just one attempt. There won't be a second attempt for CML 6, the only one that doesn't have a second attempt. Depending on how well you do on it, it will replace your worst grade of your previous CMLs, because we only consider the best 5 CMLs. So it's a good idea to do CML 6 and try to replace your worst one. Then probably increase your grade a little bit. Okay, so good luck with both of them.
Francisco.
Yeah.
What's happening with LBR3?
Oh yeah, just pass by it. It will be in 2 weeks, Alex.
Okay, so I'm all right. I did number 2.
Yeah.
And I did the other CML last week. Remember you spoke to me?
Mm-hmm. Yeah.
I did everything.
Nice.
Okay, so I'm back on track.
Amazing.
All
No,
right. I'll let you.
Sure. Yeah, anybody else? Any other question before we go to the tutorial?
The rounding errors, Francisco. I figured them out too.
Oh yeah? Oh, that's good.
Yeah.
Nice, nice.
The tour is starting now, yeah?
Yeah, no, yeah, it's already
Okay.
going, yeah.
All right, sorry. All right.
No, that's it's all good. No, perfect. All right. So I'll get going with this one. Today it will be the second one talking about simple linear regression. Let me do something here. Just 1 second. I will. So we will have, at the end of this tutorial, you should be able to describe the assumptions that underpin a simple linear regression. We'll be talking about the 4 assumptions, and they're pretty important. When you're doing simple linear regression. This is not only important in this course, but the following course, Introductory Econometrics, that a lot of you might do. Also, we'll carry out analysis of the regression residuals to test whether the assumptions hold, and carry out hypothesis tests on the slope coefficient. So we'll test during hypothesis tests to see if beta 1 is different than 0, greater than 0, is smaller than 0. All right. So let's go. Question 1. The price in thousands of dollars of 38 houses was regressed on the distance in kilometers from the central business district, CBD. It's usually CBD is the main part of cities here in Australia, or in English. So it will be the city center. And the following equation was estimated. B hat equals 486.33 minus 1.577 times distance. So this B hat is a little bit tricky, but this is not a proportion problem. This is a linear regression. And we're not talking about proportion here, we're talking about price, okay? So this P is for price, not proportion, so I hope it's not too tricky. And we have the standard error of the estimate was found to be 113.7, and the sum of squares for distance was 44,229.1. So can I please have the answer in chat? So interpret the value of the coefficient. Could you guys give it a go and see what do you think is the coefficient? Just one of these values is a coefficient. We call it coefficient, and it's the slope coefficient. Do you know which one it is? And would you like to try to interpret it? I'll give you guys a couple of seconds to see if someone wants to have a go. And exactly, Jasna. Yeah, you're right. This is the slope coefficient. And do you wanna have a go with what it means? It usually starts with an increase in distance, or in this case, 1 kilometer will we'll get going. So to interpret this minus 1.577, look at that. When distance from CBD, the little d that we have there, the big D, increases by 1 kilometer. 1 kilometer is the unit that we have for distance. The estimated price of the house B hat, which is here, decreases by $1,577. And why is it 1,000? It's because the price is in thousands of dollars, right? So although we just have a minus 1.577 here, we have to multiply by 1,000. So we have 1,000. It decreases. And of course, the most important part here, I think, is to know that it's a negative amount. So it decreases, which means the further you are from the city center, the lower the price of the house. Okay? That is the thing. Now let's let's try something else. Can you guys put down the state the units for the constant and coefficient? So you know which one's the constant and which one is the coefficient, right? Which units are we using for each of them? And let's base ourselves in what we did yesterday. I will also give you an advice. Usually the constant has to be, the constant has to be in the same units as your y variable or your dependent variable, because it's not multiplying anything. So it ends up being it's an amount that goes straight to your p hat. And the coefficient, although it will be a little bit different, it needs to transform the unit that is coming from your x variable or independent variable, right? So let's go. The constant here, B0, it's the same as P, so it will be in thousands of dollars. And our slope coefficient, B1, will be in thousands of dollars per kilometer. And why is that so? It's because the information coming from our x variable, or in this case we're calling it t, it's in kilometers. Let me do it something like that. So this, oh sorry, every time I use it, it freezes a little bit. So this little d, it's coming from here, and distance in kilometers. Oh sorry, this here, it's more clear. So that's why we need to divide it by kilometers. So we have a kilometers coming here. We want to cut both of them and end up with the thousands, which is the same as this one, which is the same as this one, which is this one. All right. Let's go. Let's keep going. Now we have the units for both. State the assumptions on which the calculations are based. So from the lectures, you have these 4 assumptions that we have for the least squares method. So linear regression is based on least squares, right? It's just a different name, but this is what we use for simple linear regression. The first assumption, we are assuming that the model is linear. Let me click one. So linearity. This means that when you plot the data, probably you can see some relationship, either positive, so upwards with the upward slope, or negative, downwards slope. And even though they are not a perfect line, they look like, if you pack them together, they look like a little bit like a line. So this is an assumption we're making, that there is some linearity. If it was a different case when you plot, if you had a scatter plot and it looks all massed like this, here you can identify kind of a line, but like the more mass, the more spread the dots are, the points are, the less you can assume it's there is a linear relationship at it. And we will be calculating a few things to see how it works. But yeah, this is what it says about the assumption about the relationship being linear. Okay. Number 2, the error terms have constant variance. So when you look at the error terms, this now you're looking at the residuals plot, which is after you draw the line, the linear regression, so the little line for the linear regression, the dots, there will be a little bit of difference, so you can plot this little difference in a residuals plot. And when you have a look at this residuals plot, to identify if they have a constant variance, for example, you could, let me use this little guy again. So cover the first half of it, of the dots. Look at this. Seems like the variance is this large, right? But when you cover the other half, it looks like the variance could be considerably smaller in here. Although there is this little point dot in there, most of the points, they can be concentrated in a much smaller area, a much smaller amplitude. So just this distance here. Sometimes they also might look like that, like a growing variance or something like that. So when that happens, this problem is called heteroscedasticity. So hetero means different, and scedasticity is this difficult word that is talking about how things are spread. Homoscedasticity, homo means equals. Then means our variance is constant like that, and heteroscedasticity, they vary, or it could be the other way around too. Okay, so that's it for the constant variance. Next one, the error terms are independent. They are not correlated or occur randomly. So this third assumption looks also in the residuals, and what you're expecting here is to have everything spread like we had for this other one, like all the dots are spread. They don't seem to have any pattern or follow any regular rule, right? Like, but look at this, like when you have your you create the residuals, but there seems to be a line there. That's something to be suspicious of. So look at this. It feels like it's still trying to, these residuals are still trying to explain something or be explained by something. So when this plot, not the scatter plot for data X and Y, this little plot, which is just a plot of these little distances here. Can you see it? So these two guys is the distance here. When this shows some pattern, then maybe the error terms are not independent. And finally, the last one is an assumption that we have that the error terms are normally distributed with an expected value of 0. So this you can assume, and for our course, we won't be dealing with it. So a normality plot is needed, and this will not be covered in ECON1310. So during our course, it's important to know these assumptions exist, but you won't be asked to evaluate if they can or cannot do this assumption. So a tricky of mine and advice, you don't need to care much about the fourth one. Let's go. During this course that we are, ECON1310, you don't need to worry much about this one. Also, for this one, you're not looking at the error, at the residuals plot or the error term. The linearity you take from somewhere else. So most of the times we'll be looking at these two guys in here. Yep. And that's it for the errors. If you guys have any questions, feel free to open your mic or send a message in chat. Let me open the chat. Nothing there yet. So let's go. So errors are independent. Yeah. Let's keep going. So we have the assumptions now. Let's test if the linear relationship is downward sloping, because we have a negative here, right? We want to test, is it really, can we say for sure it's a downward sloping using a 5% level of confidence, of significance, I'm sorry, I said the wrong thing. Confidence would be the other way around, 95%. This time it's 5% level of significance. And as a bonus for people attending or watching the tutorial later, pay attention that usually when we're talking about significance, we're talking about a hypothesis test. Okay, keep that in mind. I won't say it will be 100% of the times, but most of the times. Back to that. So let's go. To do a hypothesis test, we have 5 steps, right? So step 1, state H0 and H1. So what is it asking us? Test if the linear relationship is downward sloping. So although we have a B1, little b1 negative, we want to test if our beta 1 is also smaller than 0. Beta is the population. B1 is sample, beta is population. So we want to do evaluate the error and see if the 0 is included in that. So it's a one-tail test. Look who's coming. No, sorry. Next step, it's the decision rule, which is the module of T-calc. In this case, we use a T-table, right? Because we're basing the regression is based on a sample. So it's always a T. And also pay attention to the n-2, the degrees of freedoms is always n-2. But since it's just one-sided, one-tail test, one-sided, we can rearrange this guy because we know we're just looking at the left part of our distribution. So you know that when we're talking about T's, the numbers, both numbers will be to the left of 0. So we're talking about negative numbers here. Therefore, for a T-calc to be in a rejection region, it has to be smaller than T because it has to be all the way to the left. So we reject the null hypothesis, H0, if it's to this side, and we do not reject H0 if it's in here. Okay, that's it. And the T will be alpha, won't be alpha over 2. Why is that so? It's because it's just one-sided test. So we don't need to divide it by 2. The 5% level of significance is all the way here. So the area of this little guy, both in here, then or after the T transformation, will be 0.05. Remember, this continues the same. So let's go. We need to find T 0.05. Did I do it right? Yes. Yes. And 36 degrees of freedom. So, and remember, as I said before, n-2, we had 38 houses. Now it's 36 degrees of freedom. All right. So let's go. Can I please have in the chat the T? Can I see if you guys can find it? T 0.05 and 36 degrees of freedom. Thank you, Jasna. Excellent. Let's go. Look at that. Good job. So let's keep going. So we have a value here, but look at this little detail. Why is it negative? It's because it's to the left of 0, right? So that's why it gets a negative. Okay, so we have our T-crit. Now let's have our T-calc. Before, we used to have like x bar minus mu divided by s, the standard deviation of the sample. And today, we have a little bit different. We have this beta 1. It's the same as we had in the previous tutorial, but I don't think we looked at it in this way. Beta 1, our T-calc will be calculated with B1 minus beta 1. So x bar minus mu that we had before. And the standard deviation of our sample is S of beta 1. Let's go. What is S of beta 1? Do we have it? We can put this value, minus 1.577. One important thing, pay attention. Trying to remember if we did in a previous tutorial, but this is an important thing. The beta 1 we're testing, we're initially assuming this guy is 0 because we're testing against this number, right? So sometimes it might be a little bit like, I don't know. But if you think about what we've been doing with mu before, that's exactly what we do. We use the one that we have in the hypothesis and put down here, right? That's it then. Let's now work our S standard deviation B1. Look at that. There is a formula for it. So formula S of B1 will be our sum of squares of the estimate divided by sum of squares. SSXX. Sum of squares of X. So look where the values are coming from. We have the standard error of the estimate same here, so we can use the value there, and the square root of sum of squares for distance. Distance, D, is our X. It might be a little bit tricky here because they use D, but you remember this is the Y and this is the D. So there you go. And here we get our sum of squares of B1, okay, or standard error of B1. So let's keep going, replace the value back in there, and we get a minus 2.917. So this is the value for TCOG, this is the value for TCRIT. What is our decision? Do I reject H0? Yes or no? Can I please have in the chat? Are we going to reject H0? Is the answer for this question perfect, Jason? Yeah, perfect. It's a yes. We're going to reject the H0. So it means, as you can see, minus 2.917. This little line, it was minus 1.688. So minus 2.917 falls to the left, which is our rejection region, right? So we're rejecting H0, and we can interpret now. Conclusion. There is insufficient evidence at the 5% level of significance did I say insufficient? I think it's supposed to be sufficient, I think. Let me interpret it once again. There is insufficient evidence at the 5% level of significance to suggest that there is a negative relationship downward sloping. There is insufficient. No, it's the H1 we're saying. Sorry, it is sufficient. I apologize for this little adjustment. Sorry, my computer is just saving it. Let's go back. There is sufficient evidence at the 5% level significance to suggest there is a negative relationship. So there's sufficient evidence to reject H0, which said H0 said beta 1 is equals to 0 or greater than 0, and we're rejecting it. So there is sufficient. Okay. Yep. Apologize for this little typo there. I think if you guys let me know if you have any question regarding this one, feel free to open your mic or send a message in the chat. Otherwise, we're going to question 2. Let's see. Chat. Okay. I'll keep going. Look what we have. Now let's put our equation together. Just x beta 0, beta 1, y beta 0, beta 1, and x. All right. Let me launch the poll. We have 9 people, so I'm waiting 9 answers. So let's read it together. The manager of a discount electrical store wants to predict weekly sales based on the number of customers making purchases for a period of 15 weeks. The regression relationship between the number of customers and the sales in thousands of dollars is presented below, together with 2 residual plots, one with time and one with X on the horizontal axis. So you have the ANOVA table, as we've been seeing before. You will see the values that we have. And question 3 and question 4 are here. And basically question A is asking what we're doing in our poll. State the estimated regression equation explaining the variables. Let me have a look. I have just one answer up to now. So I will give you another 30 seconds, maybe. Is that enough? So what symbol would you give to the number of customers? What symbol would you give to sales in thousands of dollars? Then what symbol would you give to the minus 16, which is here? And you know there's an advice here, what we should be using. And finally, what symbol would you give to 0.031? Let's see. Oh, let me open it again. I have 4 answers out of 9. Let's see, another 15 seconds. So when it comes to X and Y, try to think, especially try to think which one depends on which other. So yeah, I think if I say more, I will be giving out the answer. Okay, so I'll end the poll. Done. So first, here is our equation. And what symbol would you give to the number of customers? The number of customers is our X. So nobody got it right. I changed a little bit the order here to make it a little bit more challenging than the previous ones. This is our X. For the second one, what symbol would you give to sales? It's our Y. And 2 people said it was X. I see people got confused, these 2 confused. So it makes more sense for the quantity of sales to depend on how many customers are coming to the store than the other way around. It feels like the amount of customers influence sales and not the other way around. Like, oh, the more sales, the more customers will come. It's the opposite, right? It happens in a different time in time too. Usually you need the customers so sales can happen. So that's why this is our choice for X and Y. And finally, the B0 minus 16.032 is our intercept. And our B1 is our slope coefficient. So 0.031. Okay. Let me see. I didn't even share the results. So sorry. Sharing the results if you guys want to have a look. Okay, second part. How well does the model fit the data? What was the thing we used last week to check how well the model is our regression, or simple linear regression, fit the data? How well does our axis, the variance in our axis, explain the variance in our y's? So this is going to be our R square, right? And I think we have some equations here to give us our R square. And how can we calculate it? Look, the sum of squares of the regression divided by the sum of squares of the total gives us our R squared, our coefficient. And look at this one. This is considered a moderate fit. Like it can be between 0 and 1. And when it's 0.65, it's not the best one possible, which would be 1, of course, but 65, we can interpret it like that. 65.7% of the variability in sales, Y, can be explained by the variation number of customers, X. So the more customers, since it's a positive relationship, the more sales. That's what they are saying, but it's not really strict thing. And look how it works. When it's very close to 1, our plot of X by Y would look like a line, very close. If it's 1, it will be a line. So because we're doing a simple linear regression, so to be a 1, it has to be a line. The smaller the value, the more dissipated it gets, the further from the line. In our case, it would be something more like this, I would say. But if it's very far apart, like this other one here, it's probably closer to 0. So there's a chance that there isn't even a relationship there. Okay. So that's our R squared. Now, C, once again, look, test at a 1% level, whether there is a significant relationship. He's not saying level of significance, but since it's at 1%, you know we're talking about alpha. And it's saying test, so it's a hypothesis test. A lot of advice there on what we're going to do. So first, it's not saying if it's greater or if it's smaller, if it's higher, lower, more or less, right? It's just saying test if there is a significant relationship. And as I just mentioned before, not having a relationship means being equals to 0. This slope coefficient would be equals to 0. So changes in x wouldn't change y, wouldn't explain the changes in y. So this is a two-tailed test. There's no indication if we're talking about greater or smaller, just a significant relationship. And therefore, our alpha will be divided by 2. Since they were at 1%, we have a 0.005 each side of our area. I didn't draw the other one, the beta one. I went straight to the t because that's what we're going to use. Let's go. Step 2. So our alternative hypothesis, H1 was beta 1 different than 0, tail test. Therefore, our null hypothesis, H0, would be beta 1 equals to 0. Let's go. Module, the absolute value of tcalc has to be greater than tcrit. And in this case, let's give the absolute value a value because we're testing both sides. So it's either the positive and the negative, they will be equal, just opposite signs. So we want them to be both to be greater than our tcrit, right? What is our tcrit? We get it alpha divided by 2. You get n minus 2. What is n? Look where it was, 15 weeks. So n minus 2 will be 13. And let's go to the table to have a look if we can find. Can I please have in the chat what is the value of our what is our tcrit? Thank you, Jasna. Thank you, Chiwan. Excellent. Look at that. Very good job. Thank you. So let's use the values. Look, since it's a two-tailed test, the values go to the positive side and to the negative side, right? We just took it from the table, brought it to our t distribution. Now we have tcrit. Let's find our tcalc. How do we calculate it? Look how cool is our ANOVA table. It comes with a t statistic here already. So our t statistic for B1, it's already given. So we can just plug it to our tcalc, the calculated t statistic for B1. And then we can make a decision. Step 4, make a decision. Do we reject? Can I have in the chat a yes or no? Do we reject H0? In the chat, yes or no? This is our decision rule. The absolute value. Amazing. It's a yes, Jasna. Good job. Yeah. So we do reject H0, which means there is a significant relationship there. So there is sufficient evidence at the 1% level of significance to conclude that there is a relationship between sales and the number of customers. Okay. Perfect. So question D, calculate the standard error of the estimate and explain what it represents. Standard error of the estimate. So it's our SE, this guy in here. And then we're going to explain what it represents. It's different than SB1. This is the standard error of B1, right? I think we get it from here, right? but let's go. So standard error of our estimate calculates the sum of squares of our estimate divided by n minus 2. We don't have the sum squares. Do we have it? I don't think so. We could have calculated, but there you go. We can also get it from the square root of MSE, which we have here. Look at that. We already have this value. So taking it from there, just the square root, let me take the camera from that, we get a 0.936. And this is the standard error of the estimate. And look how it works here when we're talking about the standard error of the estimate. Look, comparing standard errors, the SE, if it's a small value, it means that we did a linear regression and all in our scatter plot, all the dots are relatively close. The greater the standard error of the estimate, the further they become from, if it's a positive relation, the further it becomes. So this would be a greater SE. So SE is larger than this little one here, which is closer. And if it was a line, SE was probably going to be 0. These two numbers will be equal. A little trick here I didn't mention, but you could get SSE if you subtract 21.8604 from 33.2506. But yeah, just a little advice there, or when you're making your ANOVA table. So standard deviation of the error of all points around the estimated regression line. Hope that's clear. So let's go. Part E of question 2. Compute a 95% confidence interval for beta 1, same as we've just done in the previous question. Explain in your own words what this confidence interval represents. So here's the same slide. Here are the formulas. Let's go. So beta 1 equals to B1 plus or minus our T. It was a two-tailed test, so alpha divided by 2. And n minus 2. Oh, sorry. It was a two-tailed test. No, important thing. This is a confidence interval. It's always alpha divided by 2. Confidence interval, we're always talking about the upper, this side here in the camera, and lower downs. So it's always alpha divided by 2. Right. And then our n minus 2, because we're talking about a sample linear regression, that's our degrees of freedom, right? All right. So we know our SB1, as I said before, it's already given both our T calc as both the T calc and the standard error for B1. So there you go, the value. The only thing we need to find is this little T crit here. So let's go. Once again, in the chat, please, let's find this guy in the table. Thank you, Jasna. So 0.025, and then we go down to 13, 2.160. Excellent. There we go. Beautiful. So bringing it back here, we can just calculate our confidence interval, the lower and the upper bound. You just plug it in the calculator and you get these values. It's between 0.018 and 0.044. Very small numbers, right? But it's talking about thousands of dollars. So that's why maybe this number looks too small. The slope of the regression relationship in the population is estimated with 95% confidence to be between 0.018 and 0.044. Have a look at how we write it. Sometimes you might need to put it in a report or something. It's important to follow the standards because they can be really picky on how you write. Maybe not in this course, but probably in another one. All right. Now let's go for the assumptions. To start with, the question we have is, it is important that the assumptions about the error term are not violated in order to obtain a valid and reliable model which can be used for prediction. Assumptions of the error term. Therefore, not talking about the first assumption we have in the list, which the model is linear. Look, the error terms are below here. So observe the two residual plots that we have in here. Is there evidence that any of the assumptions have been violated? Discuss. So we're looking at residual plots. Remember, we're talking about error term assumptions, so not the first one. Also, we're probably not dealing with the fourth one. So as I said before, probably just these 2 and 3. Let's go. First one, the error terms have constant variance around the regression lines for all value of x. If you put a line, it doesn't seem to be an issue. If you try to split the, let me see what I can draw here. Format, draw this. If we try to cover half of it, seems to be following the same. Let me clear our drawing. If you try to cover the other half, there's still one outside, but when it's just one, when it's just two, you still don't consider, okay? So that's how you evaluate. But we're looking at residual plot, right? For the second or third assumption in the list, the error terms are independent. They are not correlated and occur randomly. Remember that I was talking about a pattern. If it follows, look at this. It feels like they're following, maybe not this two. I draw it a little bit, but definitely this little arch they are making here. It could be a pattern. Maybe these errors are not independent. It depends on each other. Making this line here. So probably these assumptions being violated in this residual. So error are not independent of time or not random. That's what we can conclude looking at this residual plot. It's not the normal scatter plot from X and Y. It's a residual plot, okay? It's what is left, it's the error. Finally, for the fourth one, something that we don't evaluate and we can't do it using residual plots. So errors around the regression line are normally distributed at each value of X with mean 0. For this course, we don't need to worry about it. There are other ways of analyzing it, but you don't need to evaluate. Okay. That is it for question 2. Do you guys have any question before I start question 3? Let me close this, open the chat. This is going to be our last question of our last tutorial. So feel free to open your mic, jump in and send a message or in the chat if you need. But let's go. All right. 3, let's go to our last poll for the semester, for this course. I'll stop sharing the previous one. Let's launch the last one. You guys can do it. We have, let me see how many people. 8 people. Let's get the 8 answers, right? Let me start reading them. A market researcher wishes to determine the relationship between the appraised value of houses measured in thousands of dollars and their lot size measured in hundreds of square meters for a semi-rural community. A sample of 84 was used. And then we have our ANOVA table. You remember, as we did in the previous poll, those values here. So in the questions I'm asking, what we're doing with 137.35, what are we doing with 1.49, and what are we doing with appraised value of houses? You can forget the appraised. It's just the value of the houses and the lot size. Try to think, does the value of the house explain the size of the lot? Lot is the area that we have where you can build the house on top of it. Or does the lot explain the value of the house. And depending on your conclusion, it might help you decide what symbol to attribute to this variables. Let me look. I don't want to look in the chat. I want to look in the polls. We have 2 answers up to now. Give you guys another 30 seconds. So what symbol would we give for this guy here, the intercept 137.35? What symbol would we give for 1.9? It's saying lot size here, but this is, I will give you a little bit of advice. I think it helps. It says slope coefficient. And usually when we're talking about the coefficient, we're talking about this guy here, slope coefficient. What value would we give? What symbol would we give for the appraised value of the houses? And what symbol would we give to the lot size? I can see we have 3 answers. Still have a chance of having 4 answers. I'm missing other 4. Anybody else in the last seconds to submit? 5 answers, just missing 3. Excellent, guys. Thank you so much. I'll end the poll and share the results. So let's go. What symbol would you give for 137.35? It's our B0. Very good job. 3 out of 5 of you got it right. Excellent. So second question, therefore, the 1.49. Well, first one was our intercept. So second one is our slope coefficient. We're given a B1. Let me see. B1, 3 out of 5 got it right. Great job. Finally, the appraised value of the houses, and this can be a little bit more confusing. This is the Y, and 2 out of 5 got it right. And finally, and last but not least, the lot size, which is our X, and 1 of you got it right. So it makes more sense to say the size of the lot explains the value of the house than to say the value of the house explains the lot size. You wouldn't expect the lot size to change very often, right? So it doesn't really make sense like, oh yeah, the value increased, therefore the lot size will increase. Probably not. So that's a little bit of the rationale behind how it works. Well, let's go with the exercise. Let's continue, keep going. So explain the variable. So Y is given in thousands of dollars for the appraised value of the house, and X is given in hundreds of square meters. Look at that. Where is it? Measured in hundreds of square meters. And the one above, appraised value of houses measured in thousands of dollars. This time they were more descriptive. They put down the text all typed down, no little symbols. So it's important to know how to interpret the thing, the units in this way too. Okay, so let's go. Answer in the chat. For every additional square meter of area on the lot, by how many dollars would you expect the appraised value to change? It can be a tricky question a little bit because of the units. I'm giving you an advice there. Can you guys calculate? Can I have it in the chat, please? Someone want to risk? Not seeing any brave ones sending the answer yet. So let's go. We're calculating like that. So every time you increase the lot size by 1, it would increase in our simple linear regression. We would increase by 1.49. But it's important to pay attention to the units that we have. So B1 is equals to 1.49, but for every additional 100 square meters, because that's the unit we're using for a regression, the appraised value is expected to increase by 1.49 times $1,000, which is here. equals to $1,490 for every 100 square meters. So if you just increase it by 1 square meter instead of 100, therefore you should increase the appraised value by 100 times less. At 100 times less, 1,490 is just $14.90. That's it for this one. That's the answer. Okay. Next, D. The researcher believes that a larger lot size would mean a higher appraised value. Little bit of an advice, they're larger. Test this belief at the 5% level of significance using the p-value approach. We've used the p last week. Using this test, does a larger lot size lead to a higher appraised value for the house? So let's do it. Now, once again, higher appraised value. So it's a bigger than zero relationship, because that's the question that they are making. It's not about the being equals or different than zero. It's one-sided. Therefore, our alpha is there. We're not dividing it by 2. One-tailed test. And our decision rule, let's know this guy here. Instead of using the t-crit, we'll be talking about a p-value being smaller than alpha, because remember, the p is a little area, and the p-value we're going to be seeing, if it's less than 0.05, it's to the right. It will be in our rejection region. If it's more than that, it will be we're not rejecting H0, right? Our null hypothesis. Next, alpha we know 0.05 because they're saying at a 5% level of significance. Calculating the p-value, bonus here. We have the p-value given. We don't have the t-stat here for our lot size, for our B1, but we do have the p-value. Look at it there, over there. So the problem with the ANOVA that we have to pay attention is that the ANOVA table, we plug the data, sent it to be calculated, for example, in an Excel. Excel gave us back the ANOVA table, but they don't know if our question is about a two-tailed test question or if it's a one-tailed test question. So they assume it's always two-tailed. This is something we have to pay attention. When you're dealing with the ANOVA table, this is considered a two-tailed test. So we're going to divide it by 2 when we're doing a one-tailed test. Okay, so the one coming from here is the two-tailed. Just in case that our question is a one-tailed test question or a one-tailed test, we have to divide it by 2 if it's coming from the ANOVA table. So dividing it by 2, it's a 0.258. Pretty easy. Didn't need a huge equation to do that. Let's make the decision. Are we rejecting the null hypothesis? Is the area of our p-value smaller than the 0.05? Can I please have in the chat your answer? Is it a yes or a no? Thank you, Jasna. So in this case, it's a yes. This number here, after we divide it by 2, we get a 0.0258, which is smaller than 0.05. So tricky, because like when we're dealing with the t-crit and t-calc, we want the t-calc, the absolute value, to be greater than the t-crit, because the absolute value will be to the right, or if it's negative, to the left. Absolute value, it will be like that. And in the case of the p-value, it's the area. So for the area to be in the rejection area here to the right, or when it's a two-tailed to be also to the left, it has to be smaller. That's why p-value is smaller than alpha. And in this case, we have a p-value smaller than alpha. So we reject H0. So as a conclusion, we can say there is sufficient evidence at the 5% level of significance to conclude that there is a positive relationship between lot size and appraised value. So we can say the bigger the lot size, the higher the appraised value, because it's a positive relationship here. All right, that's it. Let's go to the last item of the last question of the last tutorial. Let's talk about our assumptions. First, if it's linear, it's not something we're going to talk again, because our question is there any evidence of violation of assumptions, which would lead us to question the validity of the model? We will focus on the last one, talking about the error terms. Constant variance. First, look at our residual plot. If you split it in half and you do the thing about covering that was explained before, there's a lot more variance when the values are like 17 or smaller than there is for values that are 17 or greater than 17. Look at the range, the amplitude of our residuals. So these assumptions probably violated for this exercise. The error terms have constant variance. It's not true. They probably don't have constant variance. Okay, this is already violated. And as I said, the problem is in a heteroscedasticity problem. Heteroscedastic errors, kind of a tongue twister. And finally, the assumption number 3, there are no patterns that we can see like a line or an arch or anything. So it doesn't seem to be, the error terms doesn't seem to be correlated to each other. So they seem to be independent from each other. So there are no patterns in the residuals. So errors are independent of each value of x as well as each other. Okay. And that is it. So in this tutorial, Simple Linear Regression 2, at the end of this tutorial, you should be able to describe the assumptions that underpin the simple linear regression model. As we said, 4 assumptions. Usually the 4th assumption, it's not, we don't evaluate it here in this course, in ECON1310. And these 2 are about the error term, the 2nd and the 3rd. We evaluate it through the residual plot. And the first one, it's about if it's a linear model or not. Okay, we're assuming it's a linear model. Then carry out the analysis of the regression residuals to test whether the assumptions hold. So do we reject or not our null hypothesis, H0? And finally, carry out, oh, sorry, I said the wrong thing. Analysis of the regression residuals to test whether the assumptions hold. And finally, carry out the hypothesis test on the slope coefficient, so reject or not, H0. Okay, so thank you so much, guys, for attending this tutorial and doing so well in your LBRTs and CML. Good luck with your LBRT 3, and I'll see you in another course. Have a good one. Bye.